Stage is yours.
Thank
Thank
you.
you. Thank you.
So, good morning, everyone. Today, I will be presenting before you the work machine learning based ball size monitoring in ball mill using novel mode and feature selection methods over beamformed audio. This work has been performed with Amit Swain, Rakshit, Chirabrata Bhaumik from TCS Research, as well as Subhrajit Das, Govindha, Pavan, Tati, and Professor Arun Kumar Majumder from Indian Institute of Technology, Kharagpur. So, to begin with, if we consider the entire mineral processing chain, around 50% of energy is consumed in the grinding process itself. Now, this grinding process is carried out in a huge rotating cylindrical structure called a ball mill. So, in a ball mill, there are steel balls which rise up due to lifters inside the ball mill, and they fall on chunks of ores and breaks the ores into smaller particles. Now, what happens is that over time, these balls get worn out. That is, their size gets decreased. Now, this ball wear results in reduced grinding efficiency and increased power consumption. So, there is a need to monitor ball size. Now, the current method of ball size monitoring is using human intuition, wherein a human sits and listens to the ball mill and predicts that now it is the right time to add fresh charge of balls. The problem with this method is that if it is done too early or too late, it will either result in unnecessary downtime leading to huge financial loss or unnecessary power consumption. So we need a sensor based approach towards monitoring ball size. Now, there are contact based sensing methods such as accelerometers and probes. But the issue with contact based method is that the manufacturer may not allow you to attach a sensor to the structure of the machine because it may void the warranty. Moreover, maintenance and replacement of such sensors becomes a cumbersome process and will again result in unnecessary downtime. So we move on to non contact sensing, that is, sensing from a distance. Now, acoustics is a viable non contact sensing method. So, in using acoustics, you can observe what is happening inside the ball mill by placing the acoustic sensor outside the ball mill. Now, in the existing works, the acoustic data has been related to parameters such as mill load, mill fill level, liner wear, and particle size distribution. But ball wear is yet to be unraveled. And additionally, no study has considered the advantage of using beamformed audio over non beamformed audio. And lastly, we look into mode decomposition and feature selection. So I will get into the details in the next slides. For now, I want to say that previous works have considered these steps, but they have not selected modes or features based on physical significance of the event being observed and the target process parameter. So we address the research gaps and come up with an explainable approach towards machine learning based ball size prediction with the end objective of ball replacement planning. Now, why beamforming? So before we move on, this problem has been given to us by Tata Steel, and we are working in partnership with IIT Kharagpur. Now, this ball mill is in mineral processing lab IIT Kharagpur. So you can see a microphone array which has been placed at a distance. It has four microphones in a circular shape, and we are doing something called delay and sum beamforming. So in this, we basically delay each channel of the microphone based on the target direction of the sound source, and we sum up the channels to get a single channel. Now we have compared the raw data, that is non-beamformed data, and beamformed data over here. You can see the time series and the spectrogram. So in the spectrogram, you can see the noise gets reduced when we beamform. So And additionally, if you observe the time series, you can see that we get enhanced sound when we point the steering vector towards the toe of the ball mill. Now that we have performed beamforming, what we are doing now is that we are breaking up this single beamformed channel into multiple modes using some wavelet decomposition algorithms such as empirical mode decomposition, variational mode decomposition, and wave packet decomposition. So, in the case of EMD, you can observe that the first two IMFs, they show the impact and abrasion very well, and the third to fifth IMFs, you can hear the rolling sounds very well. In case of VMD, you get the resonant frequencies of the mill shell, and in case of WPD, you get the gross impacts. Now, if you observe the remaining modes, you can see that they don't carry much information. So it makes sense to discard these additional modes. So this will help us in reducing computation time and dataset size down the line. Now it's time for feature extraction. So before we move on, let us discuss which experiments have been performed. So we have performed experiments for 3 ball sizes, 3 ball loads, and 3 RPMs in all possible combinations. So this took 1 week, thanks to the efforts of Subhrajit and Pavan at IIT Kharagpur. So you can see the 15-second audio snippet of the rotating ball mill. So this is a single channel from the nine channel audio, and we are breaking it down into 1 second windows. For each window, we are performing beamforming and wavelet decomposition as described in the previous slides. And after this, we perform feature extraction. So we have chosen seven time series and spectral features and seven statistical features. Now, the data set looks kind of like this. So we have columns on the left side, which are basically mode feature pair. And on the right side, you have process parameters, which you already know, RPM, ball size, and ball load. And the rows represent each time window of the audio signal. So we are finding these, we know these. We can discard RPM and ball load because we are interested in predicting ball size. Now, for state of art method, we have found that there are 150 columns on the left side. Can we further reduce the number of columns? So here comes the role of feature selection. So on the top left, you can see 3 spectrograms. So here we have performed 3 separate experiments uh, for different ball diameters. So you can see as the ball diameter increases, the bandwidth of the impact region decreases. So this is our physical observation. Now let's look at the box plots beneath it. So here we are comparing, we are relating the features to the process parameter, that is ball size. Now features such as zero crossing rate or ZCR, this distinguishes the ball size very well as compared to say RMS or dynamic range. Now why? So if we go by the definition of zero crossing rate, it is the number of times the signal crosses the zero line of the graph. So if you have a high frequency signal, it will cross more number of times per second. So the zero crossing rate will be higher. Now, if you compare these plots with these values, it makes sense. So we have done this for raw audio data, that is without wavelet decomposition. Now, if we consider all the modes, this will become very time consuming, right? So we do something called feature ranking. So here we have considered all the previously mentioned feature columns with all IMF and more IMF and feature pairs. And we have chosen 3 feature ranking algorithms: ANOVA, Kruskal-Wallis, and information gain. And we have observed that, and we have taken top 15 features, In these we observe that zero crossing rate and spectral centroid top the chart. Now this matches with our previous observations, which matches with our physical observation. And now we just have 15 columns. Now the next step is ball size classification. So this is the information about the data set. So there are four data sets: raw plus EMD, raw plus VMD, raw plus WPD, raw plus EMD plus VMD plus WPD. So the state of art method considers all the modes, and here we are selecting the state of art considers all the IMFs. Sorry, and here we are selecting IMFs based on physical significance. Similarly, feature selection, the state of art uses coefficient of variation based feature selection, and here we are doing top 15 features based on ANOVA, Kruskal Wallis, and information gain. And the number of rows are proportional to the size of the experiment, that is the size of the audio and the number of ball diameters, number of ball loads, number of RPMs. And we have performed 80-20 train test split with five-fold cross validation. And we have used four classifiers: random forest, support vector, k nearest neighbors, and naive Bayes. Now, if you look over here, so these are some confusion matrices. The columns represent the individual state of art data sets, and the top one represents the beamform data set, and the bottom one represents the non-beamform data sets. You can observe that there is improvement in F1 score when beamforming is enabled. Now, this can be explained with the jump in signal to noise ratio, as you can observe here when the beamforming is enabled. Now, let us look at the F1 score closely. If you observed, the improvement is marginal. So, now what if we add the proposed IMF and feature selection? So here we are performing beamforming and IMF and feature selection. So we have compared the state of art with our proposed method. First of all, you can see that there is 10 times reduction in number of columns, obviously.
1 minute.
Yes, thank you. So there is 10 times reduction in the number of columns. And now there is a side effect of this thing. So you can observe that there is a like sharp decline in the F1 score for non-beamformed. Now, once we beamform, this drop is is getting cancelled. So uh, beamforming is enhancing the F1 score. Now here we are comparing the different classifiers for beamforming and non-beamformed. So for support vector classifier, there is a 12.8% jump in F1 score. And here we have compared the computation time for various wavelet decomposition algorithms. And we can observe that there is 50% reduction in computation time for VMD. So to conclude, we have performed machine learning, an explainable approach towards machine learning for ball size classification. We have compared the F1 scores for beamformed and not beamformed data with state of art and novel mode and feature selection methods. And we have observed that the F1 score is intact for 10%, 10 times reduction in the dataset size. In the future work, we will consider mixture of different ball sizes where we may train with a single ball size and train with mixed ball sizes and many other methods. Thank you.